You've probably noticed that in physics, problems rarely stick to just one rule. More often than not, you are going to see the law of conservation of energy and the law of conservation of momentum working together. It feels like a lot to juggle, but in this video, we're going to walk through an example to show you exactly how to apply both laws without getting tangled up in the math. Let's look at our setup. We have the yellow ball and the blue ball. The blue ball is hanging stationary at the bottom, and the yellow one is pulled back to a certain height, just waiting to be released. And once we let go, a chain reaction of physics events begins. And let's break it down into three distinct events. The first event is a swing. As soon as the yellow ball is released, it drops like a pendulum. And then the second event comes the collision. The moving yellow ball makes a head-on hit with the stationary blue ball. And finally, the third event is the aftermath. Now that both balls have speed, and they both continue that pendulum motion swinging upward. So here's our mission. We want to calculate exactly how fast both balls are moving the moment after they collide, and then determine just how high that speed will carry them as they swing upward. Now that we have the big picture, let's zoom in and solve these events one by one. Now let's dive into the first event, which is the descent of the yellow ball as it swings towards the bottom of its arc. During this phase, it's all about the energy. As the yellow ball drops, its potential energy is being converted into the kinetic energy. So the ball gains the speed. By the time it hits that vertical position at the bottom, it reaches to the maximum speed and ready for impact. Since the energy is conserved as the ball swings down, we can set our gravitational potential energy at the top equal to the kinetic energy at the bottom. Gravitational energy is the mass of the yellow ball, m2, multiplied by the gravitational acceleration, g, and the height, h. And on the other side, the kinetic energy equals to 1 over 2, then multiplied by the mass, m2, and the velocity of the ball, v2, then squared. Notice the mass m2 appears on both sides, so we can cancel it out. And this allows us to isolate v2 as the square root of 2gh. The only variable we are missing here is the height h. To find h, let's look back at our diagram and do a little geometry. The height of the ball is the total length of the rope minus that top vertical portion, and let's call that L. We know the rope is 3 meters long, which acts as the hypotenuse of that right-angled triangle. To find that adjacent side L, we just use the cosine of that 60-degree angle. So we have L equals 3 meters multiplied by cosine 60 degrees, which gives us 1.5 meters. Now, if the entire rope is 3 meters long and that top section is 1.5 meters, then the height h must be 3 meters minus 1.5 meters, and that gives us 1.5 meters. Now we can plug everything back into our velocity formula. We have v2 equals the square root of 2 multiplied by 9.8 meter per second squared, and then multiplied by 1.5 meter. And that calculation gives us 5.4 meter per second. Now we completed the first event, calculating that the yellow ball hits a top speed of 5.4 meters per second at the bottom of its swing. And next, let's move on to the second event, where the yellow ball finally collides with the stationary blue ball. Now this speed, 5.4 meters per second, we just calculated, is the initial speed for this collision. So before the collision, the yellow ball have an initial speed of 5.4 meters per second. At the same time, the blue ball is sitting perfectly stationary, so its initial velocity, let's call it v1 initial, and this speed is 0 meter per second. So these are the initial speeds before the collision. Now what we need to do is to figure out exactly how that speed is shared between the two balls after the collision. So we're looking for V2 final and V1 final. Because this is a head-on elastic collision, the ball will bounce off each other and move separately after the collision. To solve this, we can't just use one rule. The collision is actually governed by two fundamental laws. One is the conservation of momentum, and the other is conservation of energy. Now let's see how they work together to find the final velocities of these two balls. The law of conservation of momentum tells us that the initial momentum before the collision equals the final momentum after the collision. And before the collision, we have two parts to consider. We have the momentum from the blue ball, P1 initial, and also the yellow ball, P2 initial. And after they collide, we have their new momentum or final momentum, which are P1 final plus P2 final. So momentum is just the mass multiplied by the velocity. So for the blue ball, the momentum is the mass of the blue ball, which is m1, multiplied by its initial velocity, v1i. And for the yellow ball, its initial momentum is m2, multiplied by v2i. And on the right side, the final momentum for the blue ball is m1 multiplied by the final velocity, v1f, plus the final momentum for the yellow ball is m2 multiplied by its final velocity, m2f. Now let's plug in what we know and see what the mass reveals. For the blue ball, the m1 is 2 kilograms, then multiplied by its initial velocity, which is 0 meters per second. Then plus m2 is 4 kilograms, multiplied by its initial velocity, which is 5.4 meter per second. So this is the initial velocity before the collide, right? And on the other side of the equation, m1 is still 2 multiplied by the final velocity of ball 1 plus m2 is 4 multiplied by the final velocity of the second ball. So the first term of this equation is simply 0. And 5 multiplied by 5.4 is 21.6. It equals to 2v1f plus 4v2f. And this equation can be simplified by dividing 2 on each side, leaving us 10.8 equals v1f plus 2v2f. Now we have an equation where we have to solve two final velocities that are unknown to us. So we are just halfway there. To finish the job, we just need to bring our energy equation. So let's call this momentum equation the first equation. Now let's work on the energy side. Because this is an elastic collision, the kinetic energy is also conserved, right? So before the collision, the blue ball is stationary, meaning it has no kinetic energy. The yellow ball is the only source of the kinetic energy in the system. So before the collision, the kinetic energy is 1 over 2 multiplied by the yellow ball's mass, which is m2, then multiplied by its initial velocity, v2i squared. And after the collision, that kinetic energy is distributed into two new terms, one for each ball. So blue ball has the kinetic energy, which is 1 over 2, the mass of the blue ball, multiplied by its final velocity, v1f, then squared, plus the energy of the yellow ball, which is 1 over 2, m2, v2f squared. The first thing we can do is we can cancel out all the 1 over 2 in front of each term. Now let's plug in the values. On the left side, we have m2 is 4 kilograms multiplied by the initial velocity of the yellow ball, which is 5.4 meters per second, then squared, and equals to, on the right side, we have m1, which is 2 kilograms multiplied by v1f squared, plus m2 is 4 multiplied by v2f squared. This left side calculates to 116.64. It equals to 2v1f squared plus 4v2f squared. It can also be simplified if we divide each side by 2. So we have 58.3 equals v1f squared plus 2 times of v2f squared. Now we get another equation that also contains these two unknown final velocities, right? So now we have a system of two equations with two unknown variables. To solve them, we can use the substitution. From the first equation, we can find that v1f is 10.8 minus 2 v2f. And we can substitute 1 vf in this second equation for this expression. So we get 58.3 equals to 10.8 minus 2 v2f then squared plus 2 v2f squared. We can expand this term by using the identity a minus b squared equals a squared minus 2ab plus b squared. Okay, so this is a and this is b. Okay, so we get 58.3 equals, then we have a squared minus 2 multiplied by 10.8 and then multiplied by 2 v2f and then plus b squared, which is 4v2f squared. And we also have this 2v2f squared at last. And if you do all the calculations and combining all the like terms and rearrange this equation, it gives us a quadratic equation, which is 6v2f squared minus 43.2 v2f plus 58.32 equals to 0. For a quadratic equation with ax squared plus bx plus c equals to 0, x equals 2 minus b plus minus the square root of b squared minus 4ac then divided by 2a. So in this quadratic equation, we have a equals to 6, then b is negative 43.2, and c is 58.32. So plugging in the values of a, b, c, we get two roots for the velocity of the yellow ball. So we have v2f equals 5.4 meters per second, or v2f equals 1.8 meters per second. So the first root, 5.4, is exactly the same speed before the collision, and it represents the ball speed if no collision had occurred at all. Since we know a collision happened and the speed was transferred to the blue ball, so it cannot be 5.4 meters per second after the collision. So we discard this solution and keeps this 1.8 meters per second, right? So this is the speed of the yellow ball right after the collision. To find the blue ball speed right after the collision, we plug this 1.8 meters per second back into the equation 1. So we have 10.8 equals the final velocity of ball 1 plus 2 times the final velocity of yellow ball, which is 1.8 meter per second. And this gives us v1f equals 7.2 meter per second. So after the collision, the blue ball gains a velocity of 7.2 meters per second, and the yellow ball continues forward at a reduced speed of 1.8 meters per second. Now that we have completed the second event, let's move on to the third one as both balls swing upward. And now it's the energy conservation's turn again. As each ball climbs up, its kinetic energy is treated back into the gravitational potential energy until both reach their peak heights. And we need to find the maximum height or the peak height of each ball. Okay. So for event 3, we can set the kinetic energy equals gravitational potential energy. The kinetic energy is 1 over 2 mv squared equals 2, and the gravitational potential energy is mgh. Again, the mass cancels out. As we are solving the height h, we isolate h, leaving us with h equals v squared over 2g. Now let's find the h for blue ball and yellow ball individually. For the blue ball, after the collision, it gains a speed of 7.2 meters per second. So we plug in this 7.2 meters per second into this formula. We have the height for the blue ball is 7.2 meters per second, then squared, divided by 2 multiplied by 9.8. It equals to 2.65 meters. Now for the yellow ball, h2 equals, the yellow ball starts from a speed of 1.8 meters per second, and then divided by 2 times 9.8 meters per second squared, and that gives us 0.16 meters. So the blue ball reaches 2.65 meters, while the yellow ball only manages a small hop of 0.16 meters. And just like that, we've solved it. This problem might look complicated at first glance, but by breaking this motion into 3 simple events and solving them individually with the right laws, we avoided entangling all the variables together. It's all about one step at a time.